Okay, so welcome to the Thermodynamics 2 class. Okay, so this is your lecture number 5 for Thermodynamics 2. Okay, so first I will check how many students join the class. Okay, okay, so can anyone confirm that what's here on my desktop right now? So can anyone confirm?
Yes, sir.
Okay, it's lecture number 5. Okay, and chapter number 10, vapor power cycle. This screen is showing to your desktop right now?
Yes, sir.
Okay, okay, thank you. Okay, so coming towards the today lecture, so this is also related to the vapor power cycle. Okay, so previously we already look about different vapor power cycle in order to increase the efficiency and work done. Okay, so this also come under the domain of vapor power cycle for today lecture. So previously we already see about reheat cycle, how reheat increase efficiency. So we already look about different terms that how we can increase the pressure, temperature, and also the superheating temperature. Okay, so in this class also we will see another way to increase the efficiency of our power plants by using the regenerative Rankine cycle. Okay, so today lecture is about the regenerative Rankine cycle and specifically towards the ideal regenerative Rankine cycle. Okay, so the TS diagram which is shown over there is okay, so related to the Rankine cycle, which is the ideal one. Okay, so previously we already looked at there are different processes involved in the Rankine cycle, where there will be W supply to your pump, which is 1 to 2. There is a Q addition, Q in. Okay, so there will be a work out, and then there will be a heat rejection also. Okay, so but main problem with this Rankine cycle is that if you can notice that 2 to 2 dash. Okay, so this is also a heat addition process. Okay, so 2 to dash and 2 to 3 is all heat addition process. But heat transfer in the working fluid during the 2 and 2 dash at a relatively low temperature. Okay, and this lowers the average heat addition temperature and thus the cycle efficiency also. So the solution for this is if we can enhance this temperature, okay, so that the temperature of your fluid which is coming from your pump, okay, so it is already in the preheated state. For example, if we just make this 2 point over there, okay, so then our efficiency will be increased, okay, in this way also. Okay, so the idea of regeneration is only this one, that we have to enhance this point number 2 temperature. Okay, so that we can get the maximum thermal efficiency and your area under the curve also increase. Okay, so we will see that what is the advantages of these type of regeneration in it, in the vapor power cycle. Okay, so first important thing is the feed water heater. Okay, so whenever you are talking about the regenerative Rankine cycle, there is a term feed water heater which we have to install other than the 4 components. Okay, the 4 components are your boiler, your turbine, your pump, your condenser, and your the condenser and your pump. Okay, so these are the 4 components, and other than this 4, we have to add feed water heater in your regenerative cycle. Okay, so regenerative Rankine cycle is basically in the feed water heater is basically a heat exchanger where heat is transferred from the steam to the feed water. Okay, either by mixing the two fluid stream. So when there will be a mixing, it is called open feed water heater, and when it is without mixing, it is called closed feed water heater. Okay, so and the feed water, basically the feed water is the same water that is coming from your pump. Okay, so this is called the feed water. And to raise the temperature of the liquid leaving the pump, okay, so the liquid that is leaving the pump, it is called feed water before it's enter the boiler. Okay, so one solution for this is how we can increase this temperature which is entering in the boiler to transfer the heat to the feed water from the expanding steam in a counterflow heat exchanger built into the turbine. Okay, so this is the one way that we can build the heat exchanger into the turbine, and we can increase the feed water temperature, okay, from that. But this solution is also impractical because it is difficult to design such a heat exchanger, because it would increase the moisture content of the steam at the final stages of turbine. So we cannot build the heat exchanger into your turbine. Okay, so in practical, regeneration process will be carried out by using a steam plant carried by extracting or bleeding the steam from the turbine at a various point. Okay, so what is the meaning of extracting or bleeding the turbine? So it's mean that whenever we have to expand some steam in your turbine section, what we have to do is, previously we see that there will be one outlet which is from the condenser side. Now we have to just add one more outlet, okay, and we have to extract some steam which is already expanded in your turbine, and we just have to extract some portion of the steam, okay, and that portion of the steam will be used in order to heat the feed water, okay, instead of doing the work in the turbine. Okay, so this steam which we have extracted is called the bleeded steam. Okay, so we just call it as a bleeded steam. Okay, so this bleeded term come from that, for example, if in your skin, if we just punch somewhere, it will be there will be a stream of blood. Okay, so that was same process as we see in the power plant also, that if we just punch the turbine on some section, okay, so then some of the steam will be easily extracted from that portion of your of that outlet. Okay, so this steam could have produced more work by expanding further in the turbine, and is used to heat the feed water instead. Okay, so the same thing which I already told you. And the device where the feed water is heated by regeneration is called regenerator or a feed water heater. Okay, so if in any problem you can see that the regenerator is installed, okay, so it is similar to the feed water heater. Okay, so either it will be a feed water heater or it is a generator. Regeneration not only improves the cycle efficiency, but also provide a convenient mean of de-aerating the feed water. Okay, so what is the meaning of de-aeration? So de-aeration mean removing the air that leaks in the condenser. Okay, so if there will be an excess air over there will be a chances of more corrosion. Okay, so if we can just add the regeneration process, it will prevent the corrosion in the boiler also. So which is a positive thing about the regeneration process. Okay, then it's helped to control the large volume flow rate of the steam or at the final stages of the turbine due to the large specific volume at low pressures. Therefore, regeneration has been used in all the modern steam power plants since its introduction in the early 1920. Okay, so nowadays, if you can see any steam power plant practically, you will see that there will be a regeneration process is installed in it. Okay, so either it will be an open feed water heater or either it will be a closed feed water heater. You can see easily in your steam power plants also. Okay, so coming towards some advantages of the regeneration process or adding the feed water heater. So the heating process in the boiler tends to become reversible, so which is a good thing, that if it become the reversible, it's mean that we have less energy losses, or so that we can utilize more energy supplied over there. Okay, the thermal stresses set up in the boiler are minimized. This is due to the fact that temperature ranges in the boiler are reduced. So what is the meaning of this statement? For example, previously when you are working on a steam power plant without Rankine, without feed water heater, so if your T maximum is, for example, just I'm just going towards example. T maximum is 600 degrees Celsius, and your T at your pump at the outlet of your pump is, you can call it T2, which is for example 100 degrees Celsius. Okay, so if we can calculate the temperature gradient, that is the difference between this maximum and T2 temperature, so it will come to be 500 degrees Celsius. But at the same time, if we just increase the temperature of T2, for example, we just make it 400 degrees Celsius before it's entered the boiler section, then the temperature gradient is also decreased. So it's mean that we have encountered less thermal stresses on that portion also. So this is the idea behind the regeneration process also. Okay, so heat rate is reduced, so which is a good thing, and due to many extraction, there is an improvement in the turbine drainage, and it's reduced the erosion due to the moisture also. And a small size condenser is required in the regeneration process. So Some disadvantages also there. The plant become more complicated. Definitely there will be addition of feed water heater and the heat exchanger, which requires maintenance also. Okay, so that's why it become more complicated, and the cost of your power plant also increase. For a given power, a large capacity boiler is also required. Okay, and the heater are costly, and the gain in the thermal efficiency is not much in comparison to the heavier cost. Okay, so this is according to the decision of the design engineer, whether they want increase in thermal efficiency or they can just compensate with the heavier cost also. So it is according to the design specification of the power plants, which regeneration thing we have to install in. Okay, so this is how the open feed waters look like. Okay, so previously we see the Rankin cycle, which have boiler, turbine, condenser, and there will be a pump. Okay, so but now we have to add another portion, which is your open feed water heater. Okay, and we have to add two more pumps in order to pump the fluid in the open feed water heater, and one pump we have to require in order to send the feed water to your boiler also. Okay, so this is the idea behind it. So for example, the mass M of your steam is going to your turbine and it is expanded. Okay. We already talked about that we have to add one more outlet. So previously in the Rankine cycle, we only see there will be one outlet, which is you can just say that it will be 7. But now we have to add another one. Okay, so there is another one, which is your 6 outlet. Okay, so now there will be a 2 outlet at your turbine. So we have to extract the steam, some portion of the steam which is expanded in your turbine section. And for example, we just extract some, we just call it Y. Okay, so Y portion of the stream we just extracted from the turbine, and this Y fraction is called the bleeded steam. Okay, which we already extracted from the turbine. Okay, so then the remaining term, which is here, if it is going Y, so here it comes to be 1 minus Y. Okay, so rest of the steam will go towards your condenser part. Okay, so this is your mass flow. Okay, and here at point number 3, because when it goes in the feed water heater, after this it will mix and then it comes on the 3, and then your mass flow is again 1. Okay, so total it will be 1. Okay, and we will apply some energy balance equation on it in order to see that how we can thermodynamically calculate the thermal efficiency and work done from your open feed water heater. Okay, so this is how your open feed water heater looks like. So we will see in detail also. So this is how your feed water looks like, okay, in a real steam power plant. Okay, so this is the example of closed feed water heater, not an open one. Okay, so you can just, although it looks like the same, but there are some differences we will talk about in the later lecture also. Okay, so the basic principle is that here your bleeded steam is going is the inlet. Okay, so inlet of the bleeded steam, then there will be a feed water outlet, and then this will be your feed water inlet. Okay, and this is your heat exchanger part where we have to just exchange the heat between two steams. Okay, and then there will be a drainage outlet also, we will see later on when we are talking about the closed feed water heater. In this it is not available. Okay, so now coming towards the TS diagram for this cycle. Okay, so coming towards TS diagram, we will see that for example, whenever you have to analyze it, you have to build the TS diagram. I hope there will be no difficulty. Okay, so from point 1, you can start with the point 5 also, and you can start with the point 1 also. So point 5, you already know it will be a superheated state, okay, because there will be a steam. Then there will be a expansion process until point number 7. So here it will be expansion also. So you have to just draw the straight line, okay, because it is an isentropic expansion. So just from point 7, you can expand till point 7, you have to expand steam. Okay, so between 5 and 7 there is a point 6 also, so where we have to extract some bleeded steam. Okay, so bleeded steam will go in this direction, and then rest of your steam, which is going towards the downward direction towards your condenser, move towards your point 1. Okay, so the Y fraction is going towards your 6 to 3, and your 1 minus Y is going from 7 to 1, which we already discussed over there. Okay, so now from 1 to 2 we have to just isentropically compress it. Okay, so 1 to 2 it will be a isentropic process. Then at point number 3, okay, so there will be a mixing of your which is okay. So another important point is that we have to make the pressure number 6, pressure number 3, and pressure number 2 equal. Okay, the reason behind we have to make it equal, because if we cannot make it equal, the flow will not go in the right direction. Okay, so for example, if we just make the pressure of 2, we can make it higher. Okay, so it's mean that some of the portion of your blade stream go again towards your pump. Okay, so in order to make the flow in the right direction, we have to make these pressures equal, which is already seen on the TS diagram also, that P6, number 0.3 and number 0.2 is all on the same pressure line. Okay, so now coming towards your pump 3, okay, so which is installed after your mixing. So 0.3 to 0.4, there will be a pump which is after the mixing state. Okay, and number 4 point, which is this one, this pressure number 4 is equal to your P5, which is your boiler pressure. Okay, so this is the TS diagram for your open feed water heater. We will also solve one example for this, then you can, I think, better understand the physics behind the open feed water heater. Okay, so now coming towards the energy balance equation, because we have to find the thermal efficiency of this cycle also, and then we have to find fraction of steam also with the blade steam. So we will see how to calculate it. Coming towards first part is Q in. So we already know that Q in is over there between 5 to 4. So just have to H5 minus H4, you can just get the Q in part. So now coming towards Q out. So Q out is between 7 to 1, and we already discussed that your 1 minus Y fraction is moving towards from 7 to 1. Okay, so it's mean that 1 minus Y you have to multiply with H7 minus H1. Okay, and this part is Y. Okay, so now turbine out. Okay, so in the turbine out, you can see that there will be a two work from the turbine. Either one is between 5 to 6 and one is between 6 to 7. Okay, so these are the two turbine works over there. So H5 minus H6, because here the mass flow is 1, so we have to multiply 1 with it. And then 1 minus Y, because in this part it is going 1 minus Y, the fraction of the steam 1 minus Y, so 1 minus Y H6 minus H7, which is your inlet and outlet. Okay, so pump in. So there are two pumps over there. So we have to find the total pump in. So between 1 to 2, if you can just notice 1 to 2, the portion that is going from 1 to 2 is 1 minus Y. Okay, so 1 minus Y into W pump in, and then W pump 2, it's again become, the fraction become 1. Okay, total will be 1. So W pump in, the 1 will be multiply it with the W pump. Okay, so this is how you can find the pump in. Then fraction of the bleeded steam you can just find by dividing the m dot 6 over m dot 5. Okay, so m dot 5, okay, we will see from the, okay, so this is m dot 6 and m dot 5, as you can see from the diagram also. So you can divide it and you can get the fraction also. We will also see that a method of using the enthalpies in order to find the fraction of the steam in the problem whenever we have to solve the problem of the open feed water heater. Okay, so pump in, we have to find similar way, specific volume into 1, P2 minus P1. Then you have to apply the same principle for the pump 2 also. You need specific volume at 3 and P4 minus P3. Okay, so if you have any question, you can ask me also. Okay, so in this way, the thermal efficiency of your Rankin cycle increases as a result of regeneration. And then this is because we already talked about that we have just raised the average temperature at which heat is transferred to the steam to the boiler, and by raising the temperature of water before it enters the boiler. So this is the basic idea of whole regeneration process. The cycle efficiency increase as further as number of feed water heater is increased. So if we just increase the number of feed water heater, it will result in the increase in efficiency also. And nowadays many plants in operation today use as many as 8 feed water heaters. So you can easily see in the practical plants 8 feed water heater installed in it. And the optimum number of feed water heaters is determined from your economical consideration, and the use of additional feed water heater cannot be justified unless it saves more from the fuel cost than its own cost. Okay, so this is the important part of the feed water installation also. So now coming towards the question about regarding the regenerative Rankine cycle. So first you have to just read the question. So consider a steam power plant operating on the ideal regenerative Rankine cycle. Okay, so from here you can just see that it is the ideal regenerative Rankine cycle with one open feed water heater. So it is mentioned that it contains only one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius. So it means your higher pressure and temperature is given in the question. Is condensed in the condenser at a pressure of 10 kilopascal. So lower pressure is also given, which is your condenser pressure. Some steam leaves the turbine at a pressure of 1.2 megapascal. So the bleeded steam is extracted at a pressure of 1.2 megapascal. Okay, and enters the open feed water heater. So it enters the open feed water heater. So determine the fraction of the steam. So we have to find the Y, which is your fraction of the steam extracted from the turbine, and thermal efficiency of your cycle also. So this is how we can deal with this equation with the question. Okay, so now starting with the solution of this. So first we have to draw the TS diagram. So we will start and see that how you're to develop the TS diagram. Okay, so again you have to just draw from TS diagram. Okay, so this is a vapor dome. Okay, so point number 5, we already know that it will be a superheated one. So you have to just mention 0.5 over this area. So this is your 0.5. Okay, so you can start from anywhere depending on what data is available in your question. Okay, so now coming towards your expansion part. So expansion is until point number 7. Okay, so this is your total expansion. Okay, so which will be in the two-phase region. Okay, because it will going towards the condenser also. And some bleeded portion we have to extract from the point number 6. So you can draw point number 6 either outside the dome. Okay, so you can draw outside the dome also, or you can also draw inside the dome. Okay, it depends upon the data which is available on your question. So and you have to judge it when you are solving it, that either this point is number 6 is inside or outside. So we will talk about later that how we can find out that this point is inside or outside the dome. Okay, so now coming towards number 7. So this 7 will goes to your pump. Okay, that is shown over there. So this 7 goes to your point number 1. Okay, after this pump, there will be isentropic process which go towards your 2. Okay, then there will be a, okay, so the bleeded steam will be mixed at number 3. Okay, so this is your bleeded steam, and this 2, 3, and 6 pressure is equal. So you have to just draw the line like this. Okay, so now at 3 there will be again pump. Okay, so from which is also isentropic process. Okay, so just you have to draw the line straight. This pressure is equal to your boiler pressure, turbine pressure. Boiler pressure is equal to your turbine pressure. Okay, so this P5 5 is equal to P4. Okay, so this is your Y, and this is your 1 minus Y. Okay, so this is how you can draw the TS diagram. So I hope there will be no issue in drawing the TS diagram, because one section which is, I think the another section who told me that they have some difficulty in drawing the TS diagram. So I suggest you have to practice all the TS diagram by yourself. Instead, you just have to watch on the slides, or you can cannot draw by yourself. Okay, so you have to draw by yourself after the class also. Okay, so this is the TS diagram. Okay, so now we will try to solve the question. Okay, so starting from your point number 1. Okay, so we can just make it state number 1. So at state number 1, your pressure 1 is given. Okay, so pressure 1 is 10 kilopascal. Okay, it is mentioned in your question. Okay, and we already know it is a saturated liquid state, and you have to find the enthalpies H1 directly from your saturated water table against your pressure value, and that turns out to be 191.81 kilojoule per kg. So you have to find it by yourself, because I'm not going to the thermodynamics table again, because it is the same thing which we already practiced in the previous classes as well. Okay, so coming towards specific volume. Specific volume we also need in order to find the pump work. Okay, so specific volume is also at your Vf at 10 kilopascal. So it turns out to be 0.00101 meter cube per kg. Okay, so this is state 1 enthalpy and specific volume. So now coming towards state number 2. So state number 2 is your exit of your pump and the pressure is given in your question. It is same at which of your bleeded part, bleeded steam pressure. Okay, so it is 1.2 megapascal. It is mentioned in your question also. And also we also need know that it is an isentropic process and S2 is equal to S1. And you have to find your pump 1 work first. So pump 1 work will be specific volume into P2 minus P1. So you just have to put up all the values in this equation and you will get the value because specific volume come from here. P2 is given in the question, P1 is also given in the question. So after plug all the values, you will get the 1.20 kilojoule per kg. Okay, so state 2 now, and you have to find the enthalpy value of state 2 also. So H2 is equal to H1 plus W pump 1. Okay, so H1 we already find from the previous ones, which is 191.81 and plus work done by pump, which is your waste supply to your pump, equal to, you can just do the calculation, 193.01 kilojoule per kg. Okay, so point number 2, you get the enthalpy's value because you have to find the enthalpy's value at all the states so that you can find the thermal efficiency of your cycle. Okay, so coming towards state number 3. Okay, at state number 3 we already know the pressure. So pressure is again the same, which is P3 is equal to 1.2 megapascal. Okay, so again it is a saturated liquid, so you just have to find the H3 value against your pressure term in the saturated water table, and which turn out to be 798.33 kilojoule per kg. Okay, so similar way you have to also find the specific volume at 3 because you need to find the work supply to your this pump also. Okay, so specific volume at 3 0.001138 meter cube per kg. Okay, so now state number 4. So at state number 4, the similar procedure, you have to find W pump 2. Okay, and the pressure is again given because it is similar to number 5. So P5 is given, so it means P4 is also given. So P4 is equal to 15 megapascal. Okay, it is given in your question, and the temperature at temperature is also given. Okay, so we do not need the temperature. Okay, so W pump 2 is equal to specific volume at 3 and P4 minus P3. Specific volume at 3 we already find this state. Okay, and then P4 is also known to us in the question and P3 is also known to us. So by just plug in all the value, you will get the value of 15.70 kilojoule per kg. Okay, so similar procedure for your H4 also. So H3 plus W pump, now it will be 2. Okay, so H3 we already find out 798.33, which is from here. W pump 2 is from there, and you just have to add these two values and you will get 0.03 kilojoule per kg. Okay, so state 4, after this we have to move to state 5. So state 5 we already know it will be in a superheated state, and your pressure at state number 5 is given 15 megapascal in your question, and your temperature at 5 is also given, which is equal to 600 degrees Celsius. Okay, so you just have to go to superheated steam tables and find the value of H5 against this pressure and temperature, and you will get 3583.1 kilojoule per kg H5, and you also have to find the entropy value also S5 also, because we have to find the state of 0.6 by using this entropy value S5 6.6796. kilojoule per kg dot Kelvin. Okay, so just you have to note down all the values so that we can proceed for the next step. Okay, so coming towards your state number 6. Okay, so for state number 6, we do not know the either it will be a superheated or either it will be a uh, saturated vapor. Okay, so how we can find this condition for your state number 6? Okay, so first thing is you have to know from your thermodynamics 1 knowledge if your entropy value is greater than saturated entropy value, it will be in the two phase region. Okay, and if your entropy value for gaseous is less than saturated entropy value, it will be in the superheated state. Okay, so this comes from your thermodynamics 1 knowledge. Okay, so you have to just check by using the entropy value you already calculated in the state 5, that either it will be greater than Sg of state number 6 or not. Okay, if it is greater, it will be a two phase, otherwise it will be in the superheated region. Okay, and right now we already find that it will be in a superheated state. If you can just need to find out, you can go to thermodynamics table. So state number 6, P6 is 1.2 megapascal. Okay, so now you have to just S6 is equal to S5, and it is in a superheated state right now. Okay, so you have to find the enthalpy value by using the interpolation. So you have to do the interpolation by yourself. Okay, by using the entropy values and the against this pressure also. Okay, and by doing the interpolation, you have to do the first interpolation and you will get the enthalpy value 2860.2 kilojoule per kg, and also you have to do the second interpolation to find the T6 temperature also. Okay, so temperature we can find out by using the interpolation also, degrees Celsius. Okay, now state number 6, we already know the condition. Okay, so now coming towards state number 7. So state number 7, we already see that it will be in the two phase region. So state number 7, first you have for the two phase region you need okay, so P7 is equal to 10 kilopascal. You need to find the value of X, okay, which is your quality. Okay, so for quality you already know it will be S7 minus SF over SFG. Okay, so you can just plug in all the value against your 10 kilopascal and you will get the value of your so you will get the value of X7 is equal to 0.8041. Okay, so now coming towards H7, so H7 is equal to HF plus X into HFG. So HF you have to find out against the value of your 10 kilopascal, so 191.81, which you already see, and 0.8041, and HFG also you can find from thermodynamics table, which turns to be 2392.1. Okay, so just solve it and you will get 2115.3 kilojoule per kg. Okay, so all the enthalpies are right to known to us now. Okay, so now we have to go and solve the question for your to find the fraction of the steam. Okay, so our main target is to find this Y fraction, which is the bleeded steam. Okay, so how to find the bleeded steam from by using the enthalpies value. So we will see that how to solve it. Okay, so first we have to see the schematic diagram for this one. Okay, in order to find the fraction of y, we already know that this is y, this is 1 minus y, and this is 1. Okay, so you have to apply energy balance equation for this one. Okay, so we have to just okay, so you have to apply energy balance equation on this. So energy in is equal to energy out. Okay, so how much energy which is going towards it because we already know it is y, 1 minus y. Okay, so E in is equal to y into H6. Okay, so this is going in. Then another term which is going towards your open feed water heater is 1 minus y into H2. Okay, and your E out will be point number 3. Okay, and then the fraction is 1, and then it will be H3. Okay, so this is the energy balance equation for your open feed water heater in order to find the fraction of the steam, bleeded steam. Okay, so now you have to solve this equation for your y, and you will get the value of y as H3 minus H2 over H6 minus H2. Okay, so now H3 is also known to you, H2 is also known to you, H6 is also known, H2 is also known. So by just plug in all the value and you will get the, so this is 798.33 H3, 193.01 your H2, 2860.2 minus 193.01. So you just solve it and you will get the value of 0.2270. Okay, so this is your fraction of the steam, bleeded steam. Okay, so now coming towards the efficiency part. Okay, so you already know in order to find the efficiency, you have to find Q in and Q out. Okay, so for Q in, we already know that Q in is between 5 and 4, H5 minus H4. Okay, so you just have to plug in all the value because H5 is also known to us, H4 is also known to us, and you just get the value of 2769.1 kilojoule per kg. So now coming towards Q out. So Q out is between the condenser 1. Okay, so condenser 7 and 1. So this point is 7 and 1, which is your Q out. Okay, and we already know the fraction that is going towards your condenser is 1 minus y. Okay, so 1 minus y, and your H7 minus H1. Okay, so 1 minus y, just find the fraction of steam previously. So 0.2270, and H7 is also known to us, which is the 211.593, and H1 is also known to us, 921. Okay, you can solve it and you will get the Q out value as 1486.9 kilojoule per kg. So this is your Q out value. Okay, so in order to find the thermal efficiency for your regenerative Rankine cycle, so Q out over Q in, and you just plug in the value, and which is your 1486.9 over 2769.1. Okay, and that turns to be 46.3%. Okay, so this is how you have to solve the regenerative Rankine cycle with the open feed water heater. Okay, another important point over there is if you can just compare the thermal efficiency by your example 10-3. So the example 10-3 is basically the same one without your open feed water heater. So in this example, we just add open feed water heater, and for your example 10-3, the efficiency value is 43%. Okay, 43% example 10-3. Okay, so you can see by just adding one open feed water heater, you get the 3.3% increase in your efficiency. Okay, so this is how you can get the efficiency increase by using the regeneration process. So if you have any question, you can ask me now. Okay, so I hope all the things are clear now. So because you have to solve the question by yourself also at the end of this session. Okay, so coming towards your, okay, so we will go for 10-minute break and then we will again start the next portion of our lecture. Okay, and if you have any question, you can ask me as well. Okay, so we will start again. Okay, so again the topic is under the open feed water heater, but now previously we have installed one feed water heater. Now we have to add another feed water heater also. Okay, so in this case we have to add two feed water heater, two open feed water heater. So first you have to read the statement for this problem. So it is mentioned that a steam power plant operate on the ideal regenerative Rankine cycle with two open feed water heater. So it is mentioned that there will be two open feed water heater. Steam enter the turbine and it can be any number. Okay, so it will be 3, 4, 5. Okay, and then steam enter the turbine at 10 megapascal and 600 degrees Celsius and exhaust to the condenser at 5 kilopascal. So it means that your higher temperature, which is your P7 and T7, is known to you, and your lower pressure, which is your condenser pressure, is 5 kilopascal, is also known to you from question. Okay, so steam is extracted from the turbine at 0.6 and 0.2 megapascal. So there will be a two extraction process now. Previously it is a one extraction process, so there will be a one bleeded steam. Now there will be a two bleeded steam, and the pressure of both of the bleeded processes are given, which is 0.6 and 0.2 megapascal. And water leaves both feed water heater as a saturated liquid. Because it is also mentioned that the at the end of the feed water heater, it is saturated liquid. The mass flow rate of the steam through the boiler is 22 kilogram per second. So mass flow is also given. So show the cycle on the TS diagram and determine the network power output. So we have to find the power output and the thermal efficiency of the cycle. Okay, so the diagram is same, just there will be first feed water heater and this will be your second feed water heater, and there will be, okay, so now another important part is previously we looked at, for example, if your mass m is flowing towards your steam, your turbine, okay, then we have to extract some portion, which is your, for example, we just send y portion to your point 8, okay, and then we denote, for example, some portion that is coming from your 10 to 9 is z. Okay, so you can denote it from any number, either it be a, b, c. Okay, it is on you. And then the rest of your portion, which is 1 minus y minus z, will go towards your condenser part. Okay, so this is your flow of fraction from your turbines. Okay, so then if you can just notice that if this portion is z, this is from 1 to 2, it is 1 minus z, y minus z. So this portion, there will be 1 minus y. Okay, so because if you can just minus z from this term, you will get 1 minus y, and then y is coming toward your feed water 2, and then again at number 5 it become 1. Okay, so the mass flow become 1 again. Okay, so this is how you can find the fraction also. We will see that how to find the fraction in the problem also. Okay, so now we can start the problem. Okay, so we will again start with the TS diagram for this cycle. Okay, if there is any student whose mic is on, can you please turn off your mic because there's too much disturbance. Uh, okay, if any student who has the mic is on, you can just turn it off. Okay. Okay, so coming towards your TS diagram for this one with the two feed water heater. So we'll start again with the TS diagram. Okay, and you have to build the vapor dome first. Okay. Okay, so point number 7, we already know that it is in the superheated region. So just you have to mark it point number 7. For example, the point number 7 is over there. Okay, so this is your point number 7, which is in the superheated one. Okay, so for point number 8, we also do not know about it, that either it will be a, if it is mentioned in the question, it is a steam one. So then you have to just draw over there. If you cannot mention, you have to apply the check for the same entropy one. Okay, so this is point number 8. Okay, for point number 9, we also do not know about it, that either it will be inside the dome or outside the dome. So you can just mark it somewhere. For example, you can Okay, so we can just mark it inside the dome. Okay, so now the point number 10 is already in the two-phase region. Okay, so this is the total expansion, which is from point number 7 to your point number 10. Okay, so this is a straight line. Okay, so now there will be a two bleeded stream. So one is coming from your y part, 8 number. Okay, so there will be one bleeded stream. Another portion we have to extract from point number 9. So this is point number 9, and then one portion which is going from your condenser part. So there will be a 3 outlet. Okay, so now this is 10, this is number 1 because it is going from 1. So there will be an isentropic process in your pump. So this will be a straight point, point number 2. So now the pressure at your point number 3 and 2 is same. Okay, so this is your mixing one for your feed water, this feed water heater. Okay, so you just have to draw the line this because the pressure is same for 9, 3 and 2. So now coming towards your second pump, which is between 3 to 4. So again, you have to draw one line over there. Okay, so this is your isentropic process and 4, and the mixing is at number 5, and this pressure is also 4, 5 and 8 is equal. Okay, so now coming towards your point number 5 and 6. So 5 and 6 again there will be a pump, okay, which is an isentropic one, and the pressure of this pump is equal to your turbine pressure. Okay, so this is the total processes. So this is 10 megapascal, which is mentioned in your question. This is 0.6 megapascal, and this is your 0.2 megapascal, and this is your 5 kilopascal. Okay, so this is a TS diagram with the two feed water heater for your regenerative Rankine cycle. Okay, so now another important part is that we already know from 8 to 5 there is a y portion which is going towards there. Okay, so from 9 to 3 z part is going over there, and rest of the part which is remaining is going towards this section, which is your 1 minus y minus z, which we already discussed in the previous slide also. Okay, so this is your TS diagram for this cycle. So now we will start with the finding enthalpies value at all the states, because it is a tedious one, because we have to find 10 enthalpies at 10 different states. So we will start the question, because you have to note down the TS diagram also. Okay, so this is your TS diagram, so it will be more clearly shown over there. Okay, starting from your point number 1. So again, state number 1, the conditions are given in your question. At state number 1, your pressure is 5 kilopascal. So you have to go to your steam table, water tables, and you can just find your enthalpy value against this 5 kilopascal for your saturated liquid state. 137.75 kilojoule per kg is your enthalpy value. So now we have to find all the pump works. So we will start with the pump 1. So specific volume 1 is required for this. So also we have to see on the saturated liquid part for 5 kilopascal. So you will get 0.001005 meter cube per kg. Okay, so now we have to find the pump 1 work. Okay, so this is your pump 1 work, which is equal to specific volume at 1 and your P2 minus P1. Specific volume at 1 come from state 1, and then P2 is known to us, P1 is also known to us. Okay, so just plug in all the value sorry, and you will get the 0.20 kilojoule per kg. So coming towards the enthalpy value at state number 2, enthalpy value is H2 is equal to H1 plus W pump 1. So enthalpy value H1 is given from state 1. Pump 1 we already find from the previous state, and you will get the enthalpy value of 137.95 kilojoule per kg. Okay, so state 2 is also known to us now. So now coming towards point number 3. So point number 3 pressure is also given to us. So P3 is equal to 0.2 megapascal. Again, it is a saturated liquid one. So you just have to go to saturated liquid line and you can find the value H3 is equal to HF is equal to 504.71 kilojoule per kg. Similar for specific volume at 3, because we need to find the pump 2 work also. So for this we have to find the specific volume at point 3 also. So 0.001061 meter cube per kg. So the same procedure for W pump 2. So you have to multiply specific volume at 3 and P4 minus P3. So this is specific volume at 3 is given to you. P4 is also mentioned in the question. P3 is also mentioned in the question. So you can plug the value and you will get the value of 0.42 kilojoule per kg. Okay, so pump 2 is known to us. Now we have to find the H4 also. H4 we can easily find. H4 is equal to H3 plus W pump 2. And this you can just plug in the value and you will get the value of H4 as 505.13 kilojoule per kg. Okay, so now coming towards other states. So till now we have already find state number 4. Okay, so now coming towards state number 5. So for state number 5 also your pressure is given in the question. State number 5, P5 is given to you 0.6 megapascal. And it is also a saturated liquid one. So you just have to go to saturated liquid tables and you can find HF against your 0.6 megapascal and you can find the enthalpy value, kilojoule per kg. So specific volume at 5, which is equal to 0.001101 meter cube per kg. So against the same temperature, you can find the specific volume also. So for pump 3, we also find the work associated with the pump 3. So specific volume at 5 and P6 minus P5. Okay, so specific volume at 5 is known to you. P6 is also mentioned in the question and P5 is also mentioned in the question. So plug in the value and you will get 10.35 kilojoule per kg. So now coming towards state number 7. So state number wait. Okay, first we have to find the H6. So H6 is equal to H5 plus W pump 3. So H5 is known to you and and W pump already you have find out in the previous state. So you will just plug the value and you will get 680.73 kilojoule per kg. So we will start from state 7 now. So state number 7 is already on the superheated state and the pressure is known to us, which is 10 megapascal, and your temperature is also known to you, which is number 7, 600 degrees Celsius. You just have to go to your superheated steam table and find out the value of enthalpy against your pressure and temperature. So it turns to be H7 is equal to 3625.8 kilojoule per kg, and you also have to find the entropy value 6.9045 kilojoule per kg dot Kelvin. Okay, so H7 is also known to you now. So coming towards state number 8. For state number 8, you have to just apply first check for your entropy value. Either it will be greater than the gaseous one or less than. Okay, so then you can find that either it will be in the superheated state or in the two-phase state if it is not mentioned in the question. So now we will start with the state number. Okay, so for state number 8, pressure number 8 is given to you. Pressure at 8 is 0.6 megapascal. Okay, and we already know that S8, because it is an isentropic process, and then you have to go to your superhero table and you can find the H8 value easily. H8 is equal to 2821.8 kilojoule per kg. Okay, so now we are moving towards point number 9. So point number 9, pressure is again given to us, which is equal to 0.2 megapascal, and now it is in the two-phase region, so you have to apply your, and S9 is equal to S7 also, so you have to apply for your quality. Okay, so for quality, S9 minus SF over SFG. So you have all the value against the 0.2 megapascal by using thermodynamics table, and you can plug in the value, and 0.9602 will be your value for X. Okay, so now we have to find the enthalpy at state number 9. So H9 is equal to HF plus X into HFG, and you can plug in the value because HF is known to you, X9 is known to you because this is X9. Okay, so this turns to be 2618.7 kilojoule per kg by just putting all the value. Okay, so now only one state has been left now. So this is state number 10. So for state number 10, you already know that P10 is equal to 5 kilopascal. Okay, so this is also in the two-phase region. So you again have to find the X10 first. So X10 is equal to S10 minus SF over SFG. Okay, so plug in all the value, you will get the quality of 119, or similar pattern. In the similar pattern as we find the H9, you find the H10 also. Okay, so H10 is equal to 2105.0 kilojoule per kg. Okay, so now all the states enthalpies are known to us. Okay, so now we have to moving forward towards your question. So your question is to find the thermal efficiency and your power of your uh, regenerative Rankine cycle. Okay, so first we have to apply, we need the fraction of the steam, which is your bleeded steam. Okay, so how to find the bleeded steam fraction? So again, you have to apply the energy balance equation, but previously we have applied only one feed water on the one feed water heater. Now we have to apply the energy balance separately on both of the feed water heater. So starting from feed water heater 2. Okay, so if you can just correlate with your diagram, which I already shown to you in the previous slides. So E in is equal to E out. Okay, so the Y into H8 is going in plus 1 minus Y into H4 is going in your feed water 2, and 1 into H3 is going, 1 into H5 is going out. Okay, so this is your energy balance equation for your feed water heater 2. Okay, so you have to just go back and correlate with your diagram for your question. Okay, so then you can easily understand it, how you have to get this equation. So Y is equal to H5 minus H4 over H8 minus H4. Okay, so plug in all the value because you already find the enthalpy's value at all the states. So you have this value with you, 38 minus 505.13 H4, and then 2821.8, and this is 505.13 again. Okay, so this come to be 0.07133 of your bleeded steam that is going towards your that is extracted towards your feed water 2. So now coming towards feed water 1, so we have to apply energy balance equation for feed water heater 1 also, which is installed at your pump 1, at the outlet of your pump 1. Okay, so now you already see that the Z into H9 is going in towards your feed water 1, and 1 minus Y minus Z is also going in towards your feed water 1, and 1 minus Y into H3 is going out from your feed water heater 1. Okay, so now you have to solve it for Z. Okay, because we need the Z fraction, which is going from feed water heater 1. Okay, so you have to just solve this equation for Z. H3 minus H2 or H9 minus H2 into 1 minus Y. Okay, so now Y is also known to us, H3 is also known to us, all these values are known to us. You just have to plug in all the value and you will easily find the value of Z. Okay, so for Z part, we just have to apply 504.71 minus 137.95 over 2618.7 minus 137.95 into 1 minus your Y part, which is 0.07136. You already find in the previous state. Okay, so 0.1373 is your Z. Okay, so now both of these fractions are known to you. Okay, so now coming towards your thermal efficiency and your power of your Rankine cycle, regenerative Rankine cycle, you have to find first Q in. So Q in is equal to H7 minus H6, because between 7 and 6 there will be a heat addition. So you just have to add the values, which is 680.73, and after solving this you will get 2945.0 kilojoule per kg. Okay, so similar way you have to find the Q out also. So in the Q out, you already know that your 1 minus Y minus Z terms is your fraction, which you have to multiply between H10 minus H1. There will be a heat rejection process. Okay, so 1 minus, so Y is also known to you. You can just plug the value of, and this is 0.1373, which we already find from the previous state, and this one 2105.0 minus 137.75. Because you can just solve it and you can get the value of 1556.8 kilojoule per kg. Okay, so now Q out is also known to us now. Okay, so now we have to find the W out. Okay, so because we have to find the power, and the power formula is, we already know that if we have to multiply work done by your cycle with your mass flow, so you will get the power of your turbine, power of your cycle also. Okay, so work net is equal to Q in minus Q out. So Q in is also known to us, and you just plug in on the value and you will get 1388.2 kilojoule per kg. Okay, so now W net, you have to just save it. Okay, so coming towards your W net, which is your, you can just denote it like, you can just power, which is equal to M dot into your W net. Okay, so mass flow is given in the question, which is 22 kilogram per second, and W net you already find by using the previous equation, which is Q in minus Q out. Okay, so you can just plug the value 1388.2 and you can solve it for your power, and you will get 30540 kilowatt. Okay, which is equal to 30.5 megawatt. Okay, so this is the first part which you have to find, and now the second part is you have to find the thermal efficiency. So again, thermal efficiency Q out over Q in. So 1 minus Q out 1556.8, and in the denominator it will be 2945.0. Okay, so that turns to be 47.1%. Okay, so this is the solution for your regenerative Rankine cycle with 2 open feed water heater. So I hope there will be no issue in it, because just you have to select the points carefully and you have to draw the cycle on your TS diagram carefully, and rest of the things are very easy, and it is also similar to your Rankine cycle. There will be no difficulty. So if you have any question, you can ask me now. Okay, so there is no question. Okay, so coming towards your the question which you have to solve now. Okay, so this is the same question similar to the previous question. So you have to read the question first. So a steam power plant operates on the ideal regenerative Rankine cycle Steam enters the turbine at 6 megapascal and 450 degrees Celsius. So mean your highest temperature and pressure is given to you and is condensed in the condenser at 10 kilopascal. Steam is extracted from the turbine at 0.4 to heat the feed water in an open feed water heater. And waters leave the feed water heater as a saturated liquid. So in this question it is mentioned that it contain one feed water heater. Okay, so it is an open feed water heater and show the cycle on the TS diagram. So net work output. Okay, so you have to find and the thermal efficiency of the cycle. So it is an easy one because it contains only one feed water heater. So you have to apply the same knowledge and you have to send me in the inbox your ID and the snapshot of your complete work. Okay, not only the answer. So complete work, you have to just send me the snapshot, including the TS diagram also. You have to build the TS diagram by yourself, okay, on the paper. Okay, and you have to reply me in, you will take 15 to 20 minutes, you can take. Okay, so if you have any question, you can ask me now. You can note down the question also so that